So we're picking up on page 503 on goal 2. So, and it's solving logarithmic equations. So thus far, you've been solving exponential equations. And for the most part, you've been using the one-to-one property, or initially you've been using the one-to-one property, where if you can express both sides of the exponentials with the same base, you can solve them by setting the exponents equal to each other. If you can't do that, you can take the logarithm of the same base by using those inverse properties to get to release the exponent, so that where the variable is, so that you can now solve for it. All right, so in the second part, you're going to be given logarithmic equations to solve, and they're going to use a technique called exponentiation, which is taking the logarithms, still using those inverse properties, and putting the logarithms into the exponents. But let's start here at the top of the page. Okay, and I guess I already kind of told you this property earlier on, but again, so it bears repeating. It says to solve a logarithmic equation, use this property for logarithms with the same base. So that's the important thing. They got to be the same base. For positive numbers b, x, and y, where b is not equal to 1, the log of base b of x equals the log base b of y. That's that one-to-one property. You can say x equals y. Okay, so that's one technique, and then the other one is going to be exponentiation, which is using this property that basically says b to the log base b of x equals x. So that means if I have some sort of exponential function, if I have some sort of logarithmic function, I can move the logarithm up into the exponent of something the same base and get and figure out what x is. Okay, but anyway, so if you feel a little bit unclear, just we will maybe I'll leave this here for a second. Okay. All right. I better clear the whole page. Okie doke. Example 5. All right, so log base 5 of 5x minus 1 equals, oh, I'm not seeing that right. That's log base 3. Log base 3. Middle-aged eyes don't see so well sometimes. Log base 3 of x plus 7. All right, notice that these are logarithms with the same base, right? So you can use the one-to-one property by setting their arguments equal to each other. So I can simply say 5x minus 1 equals x plus 7, and then this is, you're back to algebra 1. So 4x equals 8x equals 2. And you can go back and you'll definitely want to be able to check that and see that that's the case. So yeah, both of these end up being log base 3 of 9 by the time you're done. They're both going to be equal to 2. And so you know that that's going to check out. All right, so let's read right below that example that we just did. It says, when it is not convenient to write both sides of an equation as a logarithmic expressions with the same base, you can exponentiate. Very fancy word. Makes it sound like you're doing very complicated math. G-H, each side of the equation. So in other words, they're saying if x equals y, well, then you can say b to the x equals b to the y. Okay. And the reason they're going to want to do that is that these are actually going to be logarithms that you're putting up here, and you're going to be using inverse operations then to solve for them. Okie doke. All right, so let's look at example 6. Example 6 says log base 5 of 3x plus 1 equals 2. All right, so I am going to exponentiate. I'm going to put this up into an exponent. I'm going to put that up into an exponent. What's my base got to be? Well, it's got to be the same base as this so that I can use that inverse property. So when I exponentiate, my base is going to be 5, and I'm going to put all this stuff up into an exponent. I'm using that inverse property because then all this other stuff is going to come out. And this is 5 squared. So now that I use that inverse property, what comes out? The argument here of this log. So this becomes 3x plus 1 equals 25. And now, this is just so easy to solve. And I get 3x equals 24, divide by 3, and x equals 8. And I can always test it out. I can put 8 in here, right? And I'm going to end up with 25 in here. So the log base 5 of 25, well, what is that? What do I have to raise the base of 5 to and get to 25? Well, I'll have to raise it to 2. So my check works out. Okay, now let's flip over to the next page. And we're going to look at example 7. But let's read page 504 at the very top. It says, because the domain of a logarithmic function generally does not include all real numbers, because remember, you cannot take the log of what? You can't take the log of 0. You can't take the logarithm of a negative number because you'd be taking some positive number, raising it to some base to get a negative number, which you can't do, or 0, which you can't do. So because of the domain does not include all real numbers, you should be sure to check for extraneous solutions of logarithmic equations. You can do this algebraically or graphically. All right, so let's take a look at example 7. It says log, so it's common log, so it's base 10, 5x plus log of x minus 1 equals 2. All right, now remember the section that we just did where we had the different properties. Remember this property, log of uv, remember that? Log base b of uv equals log base b of u plus log base b of v. And this property goes backwards and forwards, okay? So we're going to want to exponentiate, but before we do that, we want our logarithm here on the left to be fully condensed. So we're going to use this property. We're going back in this direction, okay? Since I'm adding these two logs, that means that these guys could be written as condensed as factors of a product that, together. So this is going to be the same thing as log 5x times x minus 1 equals 2. And of course, if I go ahead and distribute, then what is this going to be? This is going to be log 5x squared minus 5x, right, equals 2. All right, so now, next step, I am going to exponentiate. Since this is the common log, what base then do I use? Well, I'm going to use base 10. So this becomes, when I exponentiate, there's my base, and now I'm going to write log 5x squared minus 5x, and I got to exponentiate on the other side, so that's still base 10 squared. All right, so these are inverse properties, and so what comes out is this, the argument here of the log. So that's 5x squared minus 5x equals 100, and all of a sudden it looks like we got ourselves a quadratic to solve. And so I'm going to subtract the 100 on both sides. I get 5x squared minus 5x minus 100 equals 0. So next step would be that I'm going to factor out the 5 out of here. 5, and what do I get? X squared minus x minus 20 equals 0. And so now I see if I can factor this. What are the factors of negative 20 that combine into negative 1? Oh, right. Going to be negative 5 and positive 4, right? So x minus 5 times x minus 4 equals 0. And I got to keep solving for x. So what's x equal here? Well, I set that to 0, right? X minus 5 equals 0. So x equals 5. Got to do the same. Oh, wait a minute. Hold on a second. This should be a plus, shouldn't it? Yeah, okay, so that should be negative. Okay, yeah, that's right. No, I'm okay. I'm doing this late at night. Sorry, guys. All right, this should be a minus 5, and this should be x plus 4, right? That combines into negative 1. There we go. All right, so is that what I had? No. Okay, I'm doing this 11 o'clock at night. Okay, so give me a little bit of mercy. All right, so this is going to be x equals 5, okay, and then x plus 4 equals 0, so x equals negative 4. All right, so those are my two solutions, and then the question is, do they both work? Well, if I go back to my original and I put a 5 in here, that looks like it could work, right? Because I'm going to get positive numbers. But look at this x equal negative 4. It turns out that if I put in negative 4 here and a negative 4 here, I'd be trying to take the logarithm of a negative number. And so that's not going to work. So it turns out that this is extraneous. And so I'm going to have to toss it out. I'd also like you to take a look here at the book where you see the graph. You could graph both sides of the equation as well into your calculator by graphing, y equals this on one side and y equals 2 on the other side. And if you do that, assume you get the window set and everything like that so you can see it, you would find that you only have one intersection, for the solution. So that's another indication that you're getting you'd be getting an extraneous solution.